In the previous video, we laid out the framework for the simplest way to think about whether or not the electric potential energy of a charge as it moves around in an electric field is increasing, decreasing, or remaining the same. Is your charge moving with the electric force, against the electric force, or perpendicular to the electric force? In this class, we're going to focus on thinking about how the electric potential energy of a charge is changing in two different types of electric fields. And the first of those is a constant electric field. To set up how we're going to talk about the charge moving around in a constant electric field, let's think back to the constant field we know best, which is the Earth's constant gravitational field. So near the surface of the Earth, there is a constant gravitational field displayed by these field lines here. It points down. It has a magnitude of 9.8 meters per second squared. And we know that if we place a mass into that gravitational field, the force acting on that mass will point down. Which means that if I let the mass move down, it's moving with the gravitational force. Force displacement point in the same direction, so the work done by the gravitational force will be positive. But of course that means that the change in the gravitational potential energy will be negative. You've decreased the gravitational potential energy by letting your mass move down. If I now let my mass move horizontally within the field, it's moving perpendicular to the gravitational force now, which means no work is being done by the gravitational force and the gravitational potential energy doesn't change. If I move my mass back up, now it's moving against the gravitational force. So the force and displacement point in opposite directions, which means the work done by the gravitational force is negative, and that has increased the gravitational potential energy. So just like how we talked about things last semester, this is how we want to think about how the gravitational potential energy of a mass changes as it moves around in a constant gravitational field. It's very similar for thinking about how the electric potential energy of a charged particle changes as you move the charge around in an electric field. The biggest difference, of course, is I always knew the direction of the gravitational force. To figure out the direction of the electric force, I need to know what's the charge sitting on my particle. So that's the first question that we've got to ask. And so let's say that our charge here is positive. Well, if my charge is positive, then I know the electric force acting on that charge will point in the same direction as the electric field. And so in this case, if the electric field points to the right, that means the electric force will also point to the right. If I let my particle move to the right, so now the charge is moving with the electric force, the work done by the electric force is positive, and that has decreased the electric potential energy. If I move my charge perpendicular to the electric field, no work's being done by the electric force, and the electric potential energy doesn't change. If I then move my charge back to the left, in this case that means it's moving against the electric force, so the work done by the electric force is negative, which means we are increasing the electric potential energy of the charge. Once I know what the charge on my particle is, then I can figure out as it starts to move around whether it's increasing or decreasing its electric potential energy. Now, of course, positive was one option, the other option is negative. So if I have a negatively charged particle sitting in my electric field, I know the electric force acting on that charged particle will point in the opposite direction as the electric field. So in this case, the field points to the right, but the force points back to the left, acting on my negative particle. If my particle now moves to the right, it's moving against the electric force, which means it has to increase the electric potential energy. Move it perpendicular to the force, just like before, the electric force does no work and the electric potential energy doesn't change. Now when I let the particle come back to the left, it's moving with the electric force, and so the electric potential energy of my negatively charged particle is decreasing. How your particle moves is only part of the answer in terms of thinking about how its electric potential energy is changing as it moves around in a constant electric field. I also have to know what's the charge of the particle. That's the other important difference here. So let's figure out how we can calculate this out. And so let's look at a situation where, again, we've got an electric field pointing to the right. We'll let that be the positive x direction. Let's start by putting a positive charge into our constant electric field. I can start with the question, what does the electric force want the charge to do? Well, obviously the electric force is going to try and pull the charge, pull our positive charge in this case, in the direction of the electric field. It wants to pull it to the right. So if I want to calculate the change in the electric potential energy of my particle as it moves around, here's an equation I can use to do it. So notice I've got the change in the electric potential energy is equal to, there's a minus sign out front, Q is the charge of the particle that I'm moving around in the electric field. It can be positive or negative. E is the magnitude of the electric field. It's a magnitude of a vector. It always has to be positive, assuming it's not zero. And then delta x is the displacement parallel to the electric field. So in this case, part of why we've labeled this delta x is we're saying we only care about the displacement of the particle in the x direction. How it moves in a different direction, perpendicular to that we might call y, we don't care about that at all. We just care about how it's moving parallel to the electric field. And notice, just like with Q, delta x can be positive or negative. If our charge moves in the direction of the electric field, delta x will be positive. If it moves in opposite the direction of the electric field, delta x will be negative. So let's check and make sure that all that is consistent with thinking about moving with or against the electric force. So there's my equation. And so let's start by thinking about a situation in which we increase the electric potential energy. Obviously there are two ways I can do that. So an increase in the electric potential energy means that the left-hand side of my equation here has to be positive. This negative sign sitting out front on the right means that Q, E, and delta x have to give me something negative when I multiply those three things together to cancel out that minus sign. So there are two options. The E is always going to be positive. But if the Q is positive, that means I need delta x to be negative. On the other hand, if Q is negative, the negative in Q will go ahead and cancel out that minus sign there, and delta x needs to be positive. So what this means is that I increase the electric potential energy on my charge by either letting it be a positive charge that moves against the electric field or a negative charge that moves with the electric field. So Q can be positive, delta x has to be negative then, or Q can be negative and delta x has to be positive. On the other hand, if I want to decrease the electric potential energy, that means the left-hand side of my equation's got to be negative. If it's negative over here, it's got to be negative over there. And since I've got that minus sign sitting out in front, when I multiply these three things together, I need something positive. Again, E will always be positive. So this tells me that to get a decrease in the electric potential energy, Q and delta x have to have the same sign. So if I have a positive charge that moves with the electric field, I'll decrease the electric potential energy. If I have a negative charge that moves against the electric field, that will also decrease the electric potential energy. I know that decreasing the electric potential energy happens when my charge moves with the electric force. And so just to confirm that all this is consistent with everything else we've talked about, if I have a positive charge, the force will point to the right, and so if I move to the right with the electric field, sure enough, I'm decreasing the electric potential energy. If my charge is negative, the force points back to the left, and so now moving to the left against the electric field, again, decreases the electric potential energy. So you can see it's easy enough to calculate out how the electric potential energy of my charge is changing using this equation. The one downside, of course, is we just have to correctly keep track of all the pluses and minuses that are sitting over here in our values. So what you're going to see me do as a general rule to sort of get around that is to say, well, at the end of the day, once I know what this charge is, and therefore know what the electric force acting on it is, I know whether or not it's moving with or against the electric force as it moves from where it starts to some new second point. Which means I can pretty much take care of the sign right out front relatively easily. So I'm going to take care of the sign, which means I want Q, E, and that displacement to all be positively valued. So what we're doing is we're saying Q is going to go inside absolute values. I just want the magnitude of the charge, not whether it's positive or negative. E again is magnitude of an electric field, so that's always positive. And now I'm replacing this displacement in the x direction, which could have been positive or negative, with a distance that is always positive. So delta D parallel is always positive, and just like before, it only cares about the distance you move parallel to the electric field. So if this is my displacement, then there's delta D parallel. That distance is equal to the length of the displacement here. On the other hand, if I move not along the field to the right, but to the right and down, again, my displacement now has a piece that is parallel to the electric field and a piece that is perpendicular. I still only care about that distance that's parallel. So notice that whether I move to this point up here where it was initially or this point down here still gives me that same parallel distance, delta D parallel. This again is just reaffirming what we've already talked about, which is that the electric potential energy does not change if your charge is moving perpendicular to the electric field. That's why I care about that same parallel distance regardless of how much it moves up or down in this situation. The last detail, of course, is just me figuring out, well, which sign does this need? And so if it's moving opposite the direction of the electric force acting on the charge, I need the plus. If it's moving in the direction of the electric force acting on the charge, I need the minus. Now, we will often talk about the electric potential energy of the charge. And again, what that means is the electric potential energy of the charge relative to the point in the field where the electric potential energy equals zero. We never say all that, but it's always what we mean. So the electric potential energy is always a statement relative to the 0 point. The nice thing about the 0 point in a constant electric field is it works just like the 0 point did for gravitational potential energy in a constant gravitational field. We can pick where we want the 0 point to be. So I might choose to let the 0 point for the electric potential energy in this particular problem be where my charge starts. So if my charge lies along this line, then its electric potential energy is 0 because it's at the 0 point. Of course, if I want to move it off of that line, then I need a way to calculate what the electric potential energy of my charge is. And again, the electric potential energy of my charge relative to the 0 point is given by this equation. There's a plus or minus out front. We'll talk about that in a second. Again, I'm going to choose to let Q be in absolute values here, so I just want the magnitude of it. E is still the magnitude of the electric field. That's always positively valued. And again, D parallel is just the distance that I've moved parallel to the electric field. So just like what we were talking about before with that delta D, this distance doesn't care about how much you move perpendicular to the electric field. So keep that in mind. Now, with the gravitational potential energy relative to 0, it was easy to frame that as either plus if you're above the 0 point or negative if you're below it. We can still use above and below, but notice I put them in quotation marks here because the above and below works so well for the gravitational potential energy because the gravitational force always pointed down. With our charge sitting in an electric field, the electric force won't always point down, so we need to reframe this a little bit. So what above really meant was to get from the 0 point to that new point in space, you needed to move against the force. The same thing's true here. So we're going to use a plus when we go from the 0 line to some new point in space, moving against the electric force acting on the particle. Below, when we'll use a negative, that means that we're moving with the electric force acting on the particle. So as a couple of examples, let's say that our particle was positively charged. So if I want to think about the electric potential energy of this particle somewhere within this electric field, well, I know it's going to be 0 if it's on this 0 line. And since the electric force on my positive particle points in the same direction as the electric field, then moving to any points over here to the right of that line moves with the force, so these will all be negatively valued. So anywhere over here on the right, if I have a positive charge, I'll need a negative sign when I calculate the electric potential energy. On the other hand, if I'm over here to the left for my positive charge, well, to get there from the zero line, I will have to move against the electric force, and so I need a positive sign over here. If my particle has a negative charge, that flips around. So now the electric force points to the left, which means moving to points to the left, I need to move with the electric force. These now need a negative sign for the electric potential energy for this negatively charged particle relative to the 0 point. In this case, with my negatively charged particle, it's all these points over here to the right that will need the positive sign. Because to get anywhere to the right of my 0 line, I would have had to move against the electric force acting on the particle. So this is the way that we're going to reframe above and below that'll still let us figure out whether or not we need a plus or a minus in calculating the electric potential energy of our charge.